Is given by Brunella Mastrolembo. Brunella is a natural catastrophe specialist at Swiss Re in Zurich. She works mainly at the implementation of probabilistic seismic risk models for various areas of the Europe, Middle East, and Africa region and globally. Before starting her career in the reinsurance industry, about 8 years ago, she worked as a researcher in the academia, where her main focus was on modeling of Earth's crustal deformation using GPS data. Brunella holds a PhD in geophysics from the University of Bologna, Italy. And the topic is the modeling of earthquake risk for reinsurance, approach and challenges of a low-frequency phenomenon. Brunella, welcome.
Thank you. So you have seen the slide before. So thank you, and thank you everyone for being here. This is the last talk, so I know you're all here for the apéro, but I would just pretend. So I work at Swiss Re as a NatCat specialist. So you will hear this NatCat a few times probably during my presentation, and what it simply means natural catastrophes. So I work in a team where we are like around, I think, 15 people, working on modeling the different natural perils, as we call them. So hurricanes, wildfire, hailstorm, all the kind of, or most of the natural catastrophes you can think about. And my topic, my domain is, of course, on earthquakes. And I need to, yes. All right. So Swiss Re is one of the biggest reinsurance company globally. What is a reinsurance company, actually? It might be obvious for some of you, but maybe not for all. So it's simply put an insurance for insurance companies, because they also, like all of us, need to transfer part of their risk. So in case of like a big loss happen, the insurance company take part of the losses, basically. And why do we need earthquake risk models like in a reinsurance company? Because earthquake is one of the risks which is typically covered by the insurance and then by the reinsurance company as well, right? So people might buy insurance for their building to protect against like damages from the different natural catastrophes, including earthquakes. And as you can imagine, the business needs to be sustainable, so the company needs to have collected enough money, basically, through the premium over the year to be able to pay back when something happened. And to do that, the company needs to, what they want to know from us is like, how much should Swiss Re expect to pay, because in this case of like seismic risk, for that specific client and that specific portfolio in that region. So just last week, the Swiss Re Institute has published the so-called Sigma report. They publish one every quarter, I think, if I'm not wrong, right? Swiss Re colleagues confirming. And in the first of the year, they always make like a very nice summary of the year before. So now we know that in 2024, we had 328 billion losses overall, economic losses globally. And out of that, 318 billion, so 96%, come from natural catastrophes. So you can imagine that this and the rest is like man-made catastrophes. So you can see that it's like, important to know and model properly the natural perils. Now, more or less half of it was covered by insurance, and this is what you see in this plot here, right? Here we focus on the, the insured losses from natural catastrophes over time. And there are two things that we can learn from this plot. So one is the, trend upwards. So we see like a 5 to 7% growth of the losses from natural catastrophes in the last 30 years. And the other thing that we learn is from the colors of the plot, right? So the light green shows the losses, like the sum of all the losses from the weather-related perils, while the dark green shows the losses from earthquakes. Now, what we can immediately see is that, okay, there's a clear dominance of the weather-related perils. But when we look at a year like, for example, 2011, when the Tohoku earthquake happened, you might remember about the tsunami, the power plant. I mean, it was a particularly big one. But in this case, it was like the Tohoku earthquake plus a couple of big events in New Zealand in the same year, but they are enough to basically counterbalance all the losses from the weather-related perils. So the message from this slide that I want to give is that earthquakes are surely they happen with like lower frequency compared to storms and other periods, but they're still like a key contributors in terms of loss. So it's really important to understand them and model them properly. But how do we do that? How do we model quakes? So we apply this, what is called the 4-box principle. It's a quite standard, say, approach in risk modeling. This applies to quake, but also to any other, natural catastrophe. And simply means that the model is basically made of these 4 components, so hazard, vulnerability, exposure, and the financial model. I will focus on the first 3 because, the financial model is less strictly, say, related to the seismic risk per se. So let's start with the hazard. So the first question that we want to know that we want to answer to is, what is the probability that an event of a given magnitude is happening in a given region and in a given time frame? So if I ask you, is Zurich a high seismic city? What is the question that you have in your mind? Are there actually any earthquakes in Zurich, and how big they are, right? And how often do they happen? It's like a common thing, people feel quakes all the time or not? And this is the same question that we ask ourselves. And where do we get the answer is, of course, from data. Otherwise, I probably wouldn't be here presenting today. And what we look at, the most important data set that we have is history. So we look at historical catalogs. Because luckily, say scientifically speaking, earthquakes are not randomly distributed in space and time. If you look at this, this is just a map with the epicenters of the main quakes globally. You see, you can immediately see these kind of lines, which are the border in between the main tectonic plates. And so from from history, we can understand where the crustal faults are when the event happened. And that informs us on the location, let's say, of the next potential events to happen in the future. They're also not distributed randomly in time, right? So they happen each magnitude, each event of a given size happen with what so-called return period, right? So they have the average frequency. Unfortunately, this doesn't mean that we can predict when the next earthquake happens, but we know more or less the return period of these kind of events. Now, is that enough to look at history? Is that enough to look at these catalogs? Can we just give it to our underwriters, which are the colleagues that define the premium and discuss with the client? Well, not really, because this is, for example, a plot of a 1,000-year-long catalog for Europe. Each point is one earthquake in Europe, and here you have the time, and here we have the magnitude. Now, if we look at the bottom box here, it looks like there's been a quite big increase of seismicity in Europe, right? Suddenly it's becoming, we get more and more events. But this is, of course, not true, right? There's no physical reason for that. The explanation of this is simply the incompleteness of the catalogs, because while now we have instruments capturing any kind of event of any size, in the past we got the information only from people who were writing because a big event happened and they found it interesting and they were writing about that. So catalogs are incomplete. So can we just look at the last 50 years, because this will be complete? Again, not exactly, because when we look at the, say, larger magnitude, this event, so a magnitude above 8, let's say, earthquake in Europe, would just happen every few hundred years. So if we used an observation window which is too small, we could wrongly think that this kind of event cannot happen in Europe, for example, right, or in another region, and completely underestimate the risk for earthquakes. But so we need to say, be careful, look at a window, observation window, which is long enough, but keep in mind the incompleteness of the catalogs. So what we do is that we start from the historical observation. So this is an historical catalog. We complement it with other available information, so geological data, geodetic data, so GPS, and so on. From these, we can draw our model. Actually, this is not all done by myself or by the team. There's like tons of very good scientists out there. We collaborate with them. We collaborate with GEM, so the Global Earthquake Model Foundation. So we use also part of their products. So they, basically from the data, they've drawn the model. So this is like all these lines are basically all the crustal faults still in Europe, if we can stick with this example. We add the information on the frequency of the event. And what we can do is that we statistically resample basically the source model. And we can, by doing this, build synthetic catalogs of basically any length. So what you see in this last plot here is still Europe behind, you don't see it. And all like these orange bubbles are all the potential earthquakes that could hit Europe in the next 50,000 years. And this could be as long as we like. Now, as I mentioned in the beginning, we are interested in the loss. And therefore, we're interested in the damage that the earthquake creates. So far, we just have, it's important, but we have only the list of events with their location and the magnitude, right, in the previous map. But what the event, when the earthquake happened, what creates the damage is actually the shake of the ground under our building. And this is really a key parameter. So we need to also add this information into our model and really, from the event per se happening here, calculating the ground shaking that they should expect where my building is, right? So we add this information, and we add up with the final product of the hazard component, which is, this is an hazard map for Europe, right? And like with the colors, you can clearly identify the, say, higher seismicity regions, so Greece, Romania, Italy, and so on. Now, still, this is only part of the story, because of course, so in the, let's say, geophysicists and my colleagues, we kind of like to say it's not the quake that kills the people, it's the building, right? So if you were like in the desert and a very strong quake happened, it's not dangerous per se, right? So this is the next component that we need to include in the model, right? Was the second box of the one of the first slides. So this is just an illustrative slide where we compare two events that happened in 2010. So this is the Haiti earthquake of magnitude 7, and this is the Chile earthquake of magnitude 8.8. So this would be kind of the, say, comparison in terms of the size of the event of magnitude. And this is the comparison in terms of fatalities. So you see the Haiti earthquake has many more fatalities, right? Even being much smaller in terms of energy. And why? The reason is the buildings, right? So the building stock and the conditions that they had in Haiti at that time. So we are so used to see videos like, I don't know, from Japan, where we see people working at a laptop, the building is moving and they keep working. And this is like why we all expect, an event, if it hits Japan, for example, maybe we know kind of the damage is not gonna be that big, right? Because we know they kind of typically build properly and buildings which are able to resist to the quake. So this is a picture from the event 2 years ago in 2023 from Turkey that you also might remember. And this is a very quite common situation right after the event. So you see like a completely collapsed building, and all around here, there are buildings that they might be damaged for sure, but they're still standing, right? So the ground shaking between these two cannot be that different, right? They're not that far apart. So this was probably due to the building, because different building types with different materials, different number of stories, and so on, they can react very differently to the ground shaking. So this is what the vulnerability module, so the second box, is meant to model and to represent in the seismic risk models. And how do we, include that? How do we parameterize that in the model? Very simply, at least, at first glance, like using the vulnerability curves. This is just a very simple curve that shows, so on the x-axis, you have the intensity of the ground shaking. So you can imagine here, like going in this direction, the ground is shaking stronger and stronger. And here is just basically the percentage of the building that will get damaged, right? So of course, with the increase of the ground shaking, each building would have higher and higher damage. But each building or each building type has a different behavior, right? So what we have in the model in the end is like a quite big bouquet of very different curves, which are not that easy to calibrate because we would really need like data from the field, from the different, the ground shaking at that location, knowing how the building has behaved and so on. But we have data from some of the big events, so we can use them to calibrate. The last box, the third box of that 4-box approach was the exposure, right? Because once we build the model, then we feed it with the exposure, right? And this is what is typically provided to us from the client. So this is like typically a portfolio of like one client, including the list of their buildings. Now, as you can imagine here, there's another big issue with the data, because in the ideal world, we would get exactly the location of the building with all the building characteristics, so when it was built, the material, the number of stories, because this would make it different. Well, it is the case sometimes, but not always. Depends a lot on the country, on the market. Sometimes we just get some Excel file with some aggregated data. And we have to deal with that. But this, of course, includes a bit more uncertainty in the model. So the model applies some assumption in that case, so we can still cope, but of course, creates a bit of uncertainty. Now, what do we get when we put together all these amazing components and all these parameters? We get a line. So, but it's still like a very powerful line, right? It's a very important one. If we add a bit more information, so this is what is called a loss frequency curve. It's really the basis of all the underwriting and the pricing process in insurance and reinsurance company. And basically gives the expected loss in a given return period, right? So this informs our underwriters and the company so answer the first question of the first slide, right? So what is the loss that they should expect to pay for that specific portfolio of a client, for example, in the next 10 years, 100 years, 1,000 years, and so on. And based on that, they can then establish the premium. Now, I will conclude soon. The last challenge is you can imagine putting together all these parameters. They all come with uncertainty. I mentioned data. I mean, they are there, but it's also tricky to deal with them and so on. So, of course, you could have multiple curves, right? And I mean, after excluding the very unreasonable ones, okay, how do we know which of these is better, what is correct, what is wrong? Again, we would need data. So in the ideal world, we get the data from the client. So if the client had losses in the recent years, we know how many losses and so on. We can then simply add this information to the plot and then benchmark the curve and understand what is the best one among them. For quake, unfortunately, and this is what also meant in the title, is not always the case. You can imagine you ask a client who has been, I don't know, selling policies in France for quake in the last 20 years. They have no losses because there were no big quakes. So for the quakes, it's not that easy. So we need to go back in time and look at the economic losses, some estimation of events of a few hundred years ago. But as you can imagine, if you get that information, you have to translate it into today values, right? Because of the inflation, because of the urbanization. And this is actually a quite big challenge for the earthquake risk modeling compared to the more frequent catastrophes like the weather-related one. And I think, yeah, I'm done.
Thank you for this wonderful talk. We have time for one question. Are there any questions from the auditorium? Yes, the row 4.
Hi, Brunella. Thanks for the talk. I found it extremely fascinating, especially your emphasis on the uncertainty. So in the beginning, I believe around slide 6 or 7, you were discussing about this global earthquake map. and the uncertainty connected to it, given the short time frame that we have to use basically the data for predictions. So my question for you is, are these uncertainty only theoretical, or based on data from the past, the model can extrapolate to a certain level and then you assign this systematic uncertainty on top of that?
Well, I guess the question is depends on which parameters we talk about. So the way normally the seismic risk model deal with the uncertainty is that if you remember, I showed like, okay, you start from the seismicity. So for the real events, from that you kind of drone your source model, right? So it's really the fault. You assign what is called a magnitude frequency distribution that tells you for each magnitude how often you should expect a quake to hit or to happen on that fault in, depending on the region. And then basically you sample. And sample means that you add a number of combination and variation, right, to the parameters of that fault, for example, right, to the frequency, to also the, say, the formulas that we use to calculate the ground shaking. So we typically use what is called a logic tree approach, right? So you start from observation, from history, but then allow for some uncertainty and many different combinations, and you end up with so many events in your stochastic catalog, right? Because you're also including the uncertainty. So that's the way we cope normally with that uncertainty.
All right, so then you would benchmark the model down the line based on how accurate then it was on real data, or that's just a curiosity. I guess you have several steps of folding in uncertainty that comes from many of the boxes that you were building in your financial model, right?
Yeah. So we try to always kind of benchmark and validate each component individually before putting everything together. And I can tell you that it's amazing because there's so much uncertainty, but we just built the model for Europe. That's why it was the example. And when we when we saw these curves for like most of the countries and compared them to these bubbles, right, to the benchmarks that we do completely independently, we don't look at them together. When we put together, we're actually surprised that how good was the match. We still have to calibrate, but it's,
Very fascinating.
It works.
Thank you.
Thank you so much. I suggest you continue the discussion over Apero. And before we move to concluding remarks,